In this video, we're going to discuss how to convert between different base number systems. So let's start by taking a closer look at the number system that we're all familiar with, which is base 10. Now, you might not have ever really thought about why we use base 10 universally, but it's essentially because we have 10 fingers on our hands. And our digits are just symbols representing those fingers. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. And those make up our 10 digits. So whenever we get a number written in base 10, it can only have one of these 10 digits represented with it. So let's take a look at an example in base 10 to make converting between base 2 and base 6 and base 8 easier. Let's take a look at the number 2,365. To write it and have it written in base 10 means that we can break it apart as 2,000, so 2 in the 1,000s place, 3 in the 100s place, so 300, 6 in the 10s place, so 60, and plus 5. Writing it even more broken down, this is 2,000 is 2 times 1,000, or 10 to the third power. 300 is 3 times 100, or 3 times 10 to the 2 power. 60 is 6 times 10 to the 1 power. And 5 can be written as 5 times 10 to the 0 power. So that our exponents on the 10s, 3, 2, 1, 0. And if you notice, the 2,365 only used the symbols 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and no other symbols are listed here. So expanding out 2 times 1,000 plus 3 times 100 plus 6 times 10 plus 5 times 10 to the 0 is really a helpful exercise in converting to a different base. So let's discuss a different base. Let's discuss something like base 2. Base 2 you've heard of also. This is also known as binary. And binary, as you probably know, is basically the language of computers. All the little zeros and ones, which are the only digits seen in binary, toggle off or on certain aspects of a computer or computing language. So let's take a closer look at this. Let's write a number in binary and convert it to base 10. So let's say we write the number in binary 101101. And to show that this number is not in base 10, because I don't want to confuse this with the number 101,101, I want to show this is in base 2. So I'll put a little subscript of a 2 to show this is base 2. And here's how I would write this number in base 10. So we'll take the number 101101 in base 2 and convert it to base 10. And what I want you to notice is base 10 had 10 different digits possible, but base 2 will only have 2 digits possible, zeros and ones. Because base 10 had 10 different digits possible, we went 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3 for each of the possible positions. So I'm going to do the same thing with our base 2s, but instead of using 10 to the 0, 10 to the 1, 10 to the 2, and 10 to the 3, I'm going to do 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. And I'm going to stop when I get to the farthest left. So let's start here with this. We'll do first digit is 1 times 2 to the 0. So let's write that in. I want to make sure I have plenty of room. So 1 times 2 to the 0 plus the next digit is a 0 but I want to record that in there so you can follow along. I have 0, 2 to the 1s. And then, let's see, I have, so 2 to the 0, 2 to the 1. This will be 2 to the 2. So I have 1, 2 to the 2. 1, 2 to the 2. Then I have 1, 2 to the 3. 1, 2 to the 3. I have 0, 2 to the 4s, but I'm going to include that just so we can see the pattern. So 0, 2 to the 4s. And finally, I have 1, 2 to the 5th. 1, 2 to the 5th. Cool. Okay, so this is how I'm going to convert base 2s into what we're used to, into base 10. Now I just need to get out a calculator or use my arithmetic and figure out what this number is. So let's see, here we go. 2 to the 5th, remember, is 32. So this is 1 times 32 plus 0 times 16 plus 1 times 2 to the 3rd is 8 plus 1 times 2 to the 4th is 4. 0 times 2, and then 1 times 2 to the 1 is 0. Or 2 to the 0 is 1. Alrighty, let's add this all up. This is 32 plus 0 plus 8 plus 4 plus 0 plus 1. So that would be, what, 45. So the number 101101 in base 2 is equal to 45 in base 10. Now, if we're using base 10, you don't actually have to write the 10 in there. But if you're using other bases, it's important to do that. If you're using base 10, you can, but you don't have to. I want to point out, the bigger the base, the shorter the number representation. So if you have base 10, you have numbers written pretty quickly or succinctly. If you have base 2, it takes a lot longer. It takes more digits to write out a number like 45. 1011, I'm sorry, 101101 is a mouthful. 45 is much quicker. If you were looking at colors, a lot of times on computers, they're written in hexadecimal, an HTML code. I'm not going to get into hexadecimal in this video, but hexadecimal, the numbers are even shorter. Let's practice this with a couple more digits. Let's convert the following into base 2. Let's choose a simple number like 29. Now, I've written 29 in our usual base 10, and I'm going to convert it into base 2, into binary. So here's how you go back the other way. Since I'm dealing with base 2s in this case, then instead of having 10 to the 3, 10 to the 2, 10 to the 1, I'm going to have 2 to the 3, 2 to the 2, 2 to the 1. So I'm going to start with that list. And I'm going to write, let's give myself plenty of room. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. And I'm going to stop this list once I get a number bigger than 29. 2 to the 4th is 16, still too small, but 2 to the 5th is 32. So now I know I have enough 2s listed. Cool. Okay, so let's start. 32 is too big, but let's start at 2 to the 4th is 16. And what you're going to do is do 16 goes into 29. How many 2 to the 4ths go into 29? Now, you don't want to use a calculator. You want to use regular long division because you're going to want that remainder. So here we go. 16 goes into 29 only one time. 1 times 16 is 16. And when we subtract, 9 minus 6 is 3. 2 minus 1 is 1. Cool. there's our remainder. So that means that we have one set of 2 to the fourths. So I'll write 1 2 to the fourths. Okay, next one, 2 to the thirds, 8. Does 8 go into 13? Sure. So we'll do 8 divided into 13. So 8 goes into 13 one time, remainder 5. Perfect. Okay, so we have 1 2 to the third, which is 8. Okay, we'll take the remainder and go to the next one. Does 4 go into 5? Sure. So we'll do 4 divided into 5, our remainder. So 4 goes into 5 one time, remainder 1. So again, we have 1 2 to the second. Okay, next one, almost done. Ooh, 2. Now remember, each time we're doing this, we're doing 4 goes into the previous remainder. So 4 goes into 5 one time. In this case, 2 doesn't go into 1. If we tried to set that up, we would have 2 goes into 1. That'd be 0 times. So we have 0, 2 to the 1s. And we would have remainder 1 if we actually did the long division there. So last we have 1, 2 to the 1, 2 to the 0. So in binary up here, this is our answer in binary. We have 29 base 10 is equal to 11101 base 2. Cool. I think it's a good exercise to convert back. So take 11101 base 2 and make sure we get base 10. So we'll do that really quickly. This is the first, I'm going to work from the right to the left. So this would be 1 2 to the 0 and 0 2 to the 1s. Then we have 1 2 to the 2. Then we have 1 2 to the 3. 2 to the 3. Then we have 1 2 to the 4. And then we have the 1 2 to the 4. And these are all being multiplied by 1s or 0s, so that makes it pretty easy. So 2 to the 4th was 16. 2 cubed is 8. 2 squared is 4. 0 times 2 is 0. And 1 times 1 is 1. So 16 plus 8 plus 4 plus 1, sure enough, is 29. So this would be going back from binary into base 10. Let's do one last example. For this example, let's convert the number 5,284 into base 7. So remember, if I don't tell you otherwise, it's assumed to be base 10. So here we go. Now, since this is base 7s in this case, now I want 7 to the 0, which is 1, 7 to the 1, which is 7, 7 to the 2 is 49. Oh boy, get out calculator, or if you're a math teacher, you remember these things. 7 to the 3 is 343. 7 to the 4 is, I had to look this up, 2,401. And remember, I'm going to stop once I get a number that's bigger than the number I'm converting. So 7 to the 5th power is 16,807. Way too big. So since this is too big, I know that I'm good with these digits here. Cool. So since I have base 7, I'm looking for base 7. I should have the digits 0, 1, 2, 3, 4, 5, or 6. But I won't have 7s or 8s or 9s. So here we go. Remember, we're going to do division here. So we're going to take first the 7 to the 4ths and figure out how many 7 to the 4ths are represented here. So 7 to the 4th is 2,401. So I'm going to do some division. 2,401 into 5,284. And you really want to use long division here, not decimals with a calculator, because you want that remainder. The remainder is what will help you with the rest of the 7s. So I'm going to do my long division here. So let's see. 24 goes into 52. That I bet goes in twice. Yeah. So 2 times 24 is 48. And then 2 times 0 and 2 times 1. So 4802. Subtract 4 minus 2 is 2. 8, 4. So our remainder is 482. So there are 2 7 to the 4ths in there. Okay, and then do that again. Take the remainder and see if 7 to the 3rd goes into this remainder. So yeah, that's smaller. 343 should go in. So we'll do 343 into the leftovers, 482. Looks like it only goes in once. And we would subtract, that's a 9. Let's see, 7 minus 4 is 3. And then 4 minus 3 is 1. And then I'll do the same thing. Let's see, we have 1 7 to the 3rd that will go in. So I will record this one up here. And then we'll take the remainder, the 139, 49, let's see, 49, yep, is smaller than 139, so that should go in. So let's divide, let's see how many times 7 to the 2, or 49, goes into 139. Cool. And I think you know how to do long division, so I'll go a little bit more quickly. Let's see, 4 goes into 13 3 times, but I think that's too big, so it only is going to go, because it's 49, it's only going to go in twice. 2 times 18, 9, and then subtract. 9 minus 8 is 1, and 13 minus 9 is 4. Cool. So we have 2 7 squareds, so I'll record that up here. And we'll use our remainder to see how many 7 to the 1s go into 41. Cool, almost done. So 7 goes into 41. This is, I can do much more quickly. 5 times 7 is 35. And when we subtract, we get 6. So we've got 5 7 to the 1s. And then finally, last but not least, if you want to see how many 7 to the 0s, you probably don't need long division, but we'll do 1 goes into 6 6 times, remainder 0. You'll always get a remainder 0, but this number here, this remainder at your 1 spot, will always be the last digit. So we can write 21256, and I'm going to put a little base 7 to remind myself that we were dealing with base 7s, is equal to 5,284 base 10. Very cool. Now, if you want to double check, one thing that you could do is you could try, and it's probably worth a good example, to convert 21256 base 7 into base 10. Cool. Okay, so let's do that. And we should get 5,284. So here we go. Let's see. We have 7. I always start at the end, right here. So we've got 6, 7 to the 0s. And we've got right here 5 7 to the 1s. 5 times 7 to the 1s. And we've got 2 7 to the 2s. 2 7 to the 2s. We've got 1 7 to the 3. 1 7 to the 3. Put our plus sign there. And then finally, let's see, we have 2 7 to the 4s. we have 2 7 to the 4s. Cool. And then when we add this all up, this is 2 times 2,401 and 1 times 343 and 2 times 49. And oh, this one I can do. 5 times 7 is 35 and 6 times 1 is 6. Add that all up and you can double check me. Please do. You should get 5,284. And yes, that guy is base 10, but if it's base 10, you don't have to write the base in. Only if it's a base that's different than what we're used to, base 10. Very cool.